Okay, at this point, if you can't see my screen, please just let me know. And then if everyone can see it, we can go ahead and get started. And then just so you guys are aware, Dustin asked this in the last session. It was just like, do you prefer me typing in the answers or talking them out loud? Doesn't matter to me. Whatever you guys find easier to do. Also, I look kind of a mess today. Let's just ignore that. All right. So, do you want to start up here with naming, or do you want to go down to like the exam-like questions, like the multiple choice ones and everything? Hello, Carissa. We're just getting started. We're doing chapter 13 practice problems. The exam-like ones? Okay, so honestly, this is similar to something you'd get on the exam, but we've done this one before, so you know what? Fine, let's just review it. Okay, in this kind of reaction, this is a 1,2,1,4 addition. And the nucleophile would be which one? And then while you guys type that in, the nucleophile, remember, is the one that is attacking. Yes, A is going to be the nucleophile because it attacks the hydrogen. And then number 11, the electrophile. So the electrophile is the one that is being attacked. So which one is the electrophile? B. Yes, I agree. Cool. So now this set specifically asks for the kinetic in the 1,4. So really quick, what defines the kinetic product? Faster, yeah, that's the one that forms faster. But faster and slower are not necessarily the words I would use, only because they could ask you a question that's phrased like, which product is going to form faster at high temperatures? Right? And so now it's like, okay, well, are we talking about the kinetic or are we talking about higher temperatures, right? So I would say which one, sorry. So I would say do the least number of steps. Exactly. So it is the one that's forming faster, but for the purposes of just like technicality, I'm going to say formed in the least number of steps. And what's the other part of this? Like, let's say you were looking at a reaction diagram. How would you be able to tell? Yes, it has the lowest activation energy. Perfect. So then just for comparison purposes, what about the thermodynamic product? How do we know something is a thermodynamic product? Lowest potential energy, perfect. And something else? More stable, exactly. So it's the most stable product. And in these reactions specifically, when we're talking about stability, what are we looking for? Like what tells me which one of these is more stable? More substituted, awesome. And then that brings up a great question, Dustin. So most substituted double bond. Good. Okay. And so basically what Dustin asked is, how do we know how high or low the activation energy is? So that's a really good question. When we're looking at something like this, so if he gave you this reaction mechanism and he asked you two questions like, find the kinetic product and the nucleophile, right? You wouldn't be able to find the lowest activation energy or potential energy necessarily, because like they don't give you a reaction diagram, they just give you this. So what you would have to look for is, what does this mean? The one that's formed in the least number of steps. So you could tell that if we were to draw out the reaction mechanism and we were to steal that hydrogen, we would get a carbocation here. So the 1,2 product is the one that's made in fewer steps, whereas here we had to do resonance. So they're not giving you the activation energy, but when you're able to see that this one was the one that was formed in the least number of steps, you know that this one will then have the lowest activation energy. Does that make sense? And then it's the same. Okay, cool. And then it's the same for potential energy. Like, it's not going to tell you the potential energy, but this double bond is tri-substituted versus this one is di-substituted. So from that, you can figure out that this one would have the highest potential energy. So I kind of gave it away already. It have the lowest potential energy. So this would be the most stable. I already gave it away. So the kinetically controlled product in this case would be D, because it's being formed in the least number of steps. But when we're talking about 1,2 versus 1,4, that's completely just like a naming thing, right? We look at, I don't know why it just gave me that notification about my AirPods, but whatevs. Yes, so we know that that's just based on counting. So which one of these is the 1,4 product? C, awesome. So 1, 2, 3, 4 versus 1, 2. And then that's pretty much everything he could ask you about this type of question, or this kind of reaction. He could also possibly say like, what type of reaction is this? So if he were to ask you what type it is, this is an addition to conjugated systems. I don't know if we talked about that in SI, but just in case he asks you, that's what it is. And yes, so Taylor asked if I can go through the steps to get to the 1,4 product, and I can definitely do that. So please don't mind my pet screaming in the background. Okay, so if we go bam, bam, the first thing we're going to do is we're going to add the hydrogen, and we're going to assume everything is like a Markovnikov addition. So the hydrogen is going to go to the least substituted side, and we end up with a carbocation here. If we were to just add the bromine at that point, we would get the 1,2 product, but we could also do resonance right here. And that resonance is not going to change the hydrogen. The hydrogen stays exactly where it was, but it's going to change the plus, because now our double bond has moved here. So in the next step, when bromine finally attacks, it's going to attack all the way over here at the carbocation. Wow, that's ugly. And we get HBr, and we get our double bond here. Was that okay, Taylor? Any questions? Good. All right. Cool. So then let me just zoom out so if you needed anything, you could see it. And then let me know when you are ready to move to the next question. Oh, you know what? There is one more type of question he can ask you. Pretend this isn't here. He could give you a reaction coordination diagram. We'd say A, B. And the question will say something like, at equilibrium, blah, 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 which of the following is true? So, equilibrium, what does that tell us about the reaction? Yes, so equilibrium tells us that it is under thermo control. And like to go even further with that, it means that we favor the most stable product. Because we know the thermodynamic product is the one that has the most stable double bond, right? So if he gives you this diagram and he says which of the following are correct or which of the following are true, it'll be something like B is favored, A is favored, the activation energy for A is higher than for B, you know, like phrases like that. And the correct answer would be activation energy. Which one of those is the kinetic product? Ignore my dad coughing in the background. Hey, exactly. So this one is the kinetic because it has the lowest activation energy. Cool. And then potential energy is going to be this line right here. And that just tells you the stability of the product. So which of those products are more stable? Also, hello, Anthony. I don't know when you joined, but I just saw you pop up. A again. Awesome. So this is also the thermo product. So what can we say about this energy diagram? Well, we can say that A is kinetic and thermo. We can say that A is formed, or we could say A is favored. And we can also say that the most stable product is made the most rapidly. What the heck does that mean? Well, this is the more stable product. It has the lowest activation energy, and it's thermodynamically controlled. So we know that the most stable product is favored, and it's made the most rapidly. So hint, hint, nudge, nudge. If he were to ask you a question like this, just know these are the different ways he could word the correct answer. And then someone said that they're glad my family's doing okay. Thank you. I appreciate it. Yeah. My dad is like still coughing his lungs out, as you can hear in the background, but like he's not sick anymore. He just has the residual cough, and I'm like, yikes. And then this is not funny. I was gonna say this is really funny, but it's not funny. But he is immunocompromised, so when I was like, oh, he's sick, in the back of my head I was like, hope he doesn't like die, but he's fine. So we're chilling. Anyway, I'm gonna stop talking. Any questions about this reaction or anything before we move on? Cool. So this is a related question. What's the most important part of this question? You're right, the answer is D, but why? What's the important takeaway from the question? High temps and reversible conditions. So don't forget, reversible conditions, aka equilibrium, those both mean thermo. If this asked you about the lower temperatures, what would the answer be? Kinetic, exactly. So high temps, thermo, low temps, kinetic, and 1-2 control and 1-4 control are not even a thing. So, garbage. All right, so now let's go on to these fun questions. And actually, I'm going to go into my handout right quick because I have some good exam-like questions. Nah, don't look. Don't look, don't look, don't look, don't look, don't look. Okay. So, where did I post the videos? For, like, the concept videos, you mean? Or, like, the, SI sessions and stuff? Because they should all be on the YouTube channel. I might not have added them to the playlists yet, but I definitely uploaded them. One of them doesn't have any audio, and I don't know why, but... Okay, so he'll have something similar to this where he'll have like 4 or 5 choices and he'll say like, which of the following is a diene? So I'm just going to point at a couple of these and you tell me whether it's a diene or a dienophile. This one. Right here. Yes, it's a dienophile because triple bonds have to be dienophiles. Cool. What about this one? And yes, I can definitely explain the difference. So let me give you this awesome thing that I made in previous semesters because I don't want to redraw it. And I'll show you the top and then I'll scroll down to the bottom. So a diene is going to literally be any conjugated diene. So anything that looks like this, right? And the diene is going to be the nucleophile. So it's the thing that does the attacking. And in order to react, it has to be like this. It has to be S-cis. Or it has to be able to turn into S-cis. So let's say we have this. We can rotate the single bond in the middle and we can turn it to S-cis. Versus if we're locked in a ring or if we have tert butyl, you can't rotate. So these would not react. This is a good thing to note because he loves to ask you a question with these guys and you have to know that it won't react. And I can show you an example of how he'll ask that in a second. But additionally, the diene wants electron donating groups because those electron donating groups donate electrons to the diene, and then the diene has more electron density, so it has more electrons to attack with, so it's a stronger nucleophile. Versus the dienophile is going to be any alkene or alkyne, so any double or triple bond. And as far as like configuration goes, so it doesn't have to be a specific configuration. It's not going to have S-cis or S-trans, so you don't, it could be whatever. All you need to take note of is whatever you start with, you're going to end with that. So if you have a trans double bond, you're going to end with a trans product. If you have a cis double bond, you're going to end with a cis product. And then it wants electron withdrawing groups because it is the electrophile. So electrophiles want to be positively charged. They want to have like less electron density so they can be attacked. So having those electron withdrawing groups pulls away all that electron density, and you're able to then attack it because it's a better nucleophile. I lied. It's a better electrophile. And then I can go back to that if you want, but I just wanted to show you guys real quick. Electron donating versus withdrawing groups. So we talked about this before, but I did just want to show you the drawing that I had done because this has a little bit more information on it. So electron donating groups are anything with lone pairs or negative charges, or R groups. And then withdrawing groups have positive charges, halogens, carbonyls, things of that sort. So do we feel better about diene versus dienophile and what that entails? Ow. I'm cracking my knuckles and like my fingers just hurt so bad for no reason. Besides the fact that I'm cracking my knuckles like 18 times a day. Alright, does anyone want me to stay here? If not, I am going to jump back to the last thing. Justin was so fast to be like, no, can we move on? This is fine. There we go. Alright, so what about this one? What do we think about this one? Diene or dienophile? Dienophile, cool. But which part of it? Is it the double bond or is it the triple bond? The double bond. Okay, awesome. So this triple bond is just here to kind of trick you. So this is an electron withdrawing group. It's not the part that acts like the dienophile because this is a nitrogen. And in order to be a diene or a dienophile, you have to just be dealing with carbons. So it would have to be a triple bond like this, or like OH or whatever. Some other group has to be away from the triple bond. Versus the nitrogen is like right on the triple bond. So, what about this one? Diene. Cool. Okay. Seems like you guys have a pretty good grasp of what's what. So, which of the following will be the most active dienophile? So, please remind me. Dienophiles like what kind of group? Donating or withdrawing? Yes, they want electron withdrawing groups. So, what this question is really asking you is which one of these guys has the strongest withdrawing group on it? So which one of these would you kick out immediately? So which one of these is the worst answer? A, yes, I totally agree with you. A is out because this isn't even a dienophile. This is a diene. So that sucks. Now we have to compare groups. So we have 2 carboxylic acids, 2 ethers, and then just this R chain. So B, first of all, is this a donating or withdrawing group? Ooh, this is one of the ones I said we have to be careful with. Okay, so if we have a carbonyl and it's attached like this is an electron withdrawing group because it's attached at the carbonyl. But if it's attached like this, then it's going to be an electron donating group because this has a lone pair. So whenever you see a carbonyl, if it's donated at the carbonyl carbon, if it's attached at the carbonyl carbon, it's a withdrawing group. If it's attached at the oxygen, it's a donating group. So this is electron withdrawing. Now, based on what I just said, this oxygen is going to be what kind of thing? And oh, okay, before we move on, I will explain that one more time. There was a big stutter there. So, carbonyls. If it's attached like this, where whether this be a diene or a dienophile, it doesn't matter. If it's directly attached to the carbonyl carbon, this is going to take electrons away from the system. And we consider this the system. So it's pulling electrons away from the system. It's electron withdrawing. Versus if it's attached to the oxygen, yes, this oxygen does resonance this way, but also it has a lone pair, and that lone pair can donate into the system. So we're going to call that donating. So carbonyls are the only ones that are a little bit tricky. If the carbonyl carbon is attached to your group, such as in this example, that means it's a withdrawing group. If it was attached to the oxygen like this, or, you know, any time the oxygen is attached, that becomes a donating group. So, like Anthony said, wait, no, I lied. Wait, does that concept make sense so far? Yes, okay. So the next thing. This guy has a lone pair. And we know that lone pairs can donate their electrons into the system. So this one would be an electron donating group. And it donates with resonance. And the only reason I point that out is because this is also an electron donating group. Our groups are donating groups, but they donate with inductive effects. I'm going to say donate with induction. So this is a strong donator. This is a weak donator. Sorry if everything's like on top of each other. I can start erasing things if you want. But does this sort of kind of make sense? Like why I assigned each thing? Yes? Okay, swaggy. So, out of these answers, which one would be the best dienophile? B, exactly, because it's the only one that has a electron withdrawing group. All right, so the next question is asking, which of the or actually, does anyone need me to stay here? Right. So I know it's like 6 p.m. and I'm never going to be able to go to sleep, but I paid like $5 for this coffee, so now I have to drink it. And this is why I am the way I am. So which of the following is the most reactive dienophile? So it's the same exact thing we did in the last one. I'm going to give you guys like a minute to look at this and decide like what groups are in what category, and then we'll go over it together. And then if anyone has any questions, you can let me know. So I'm just going to mute myself for a minute. Alrighty, so it's been like approximately a minute. Does everyone have like, did everyone get a chance, I should say, to at least look at this? Yeah, okay. I got a couple yeses, so that's good. Alrighty, so walk me through it. Number one, what are these substituents considered? And I can highlight the substituents for you. What kind of groups are these? Electron donating or electron withdrawing? Donating groups. Awesome. So these are electron donating groups. And we have times 4. And the reason I write that is because this one has the same donating groups, but only times 2. This one we're not necessarily putting in order, so it doesn't really matter. But if he was asking you to put it in order, I'll tell you the logic behind that. Okay, so number 2. Is that a donating group or a withdrawing group? I got one answer so far. Okay, so someone said withdrawing, right? And I know that a lot of people are thinking the same thing. Ooh, but another person said donating. All right, so let's talk about it, right? So, what were the main things we talked about for electron donating groups? Like, what were the main things I highlighted in that little chart? Lone pairs, and there were 3 big things, but if you only remember 2 of them. Lone pairs, R groups, yes, and negative charges. Awesome. So this one, even though it looks like it's going to be withdrawing because it is really electronegative, it has a lone pair. So it has to be an electron donating group. And then what about the 2 methyls? Well, you guys already said it, so I'll just give it to you. These are also electron donating groups. All right, so what about CN? What do we think about CN? Withdrawing group. Cool. I totally agree with you. They are withdrawing groups because the nitrogen triple bonded to a carbon is going to be extremely electron withdrawing. So which one of these is the best dienophile? Number 3. Which one would be the worst dienophile? We're torn between 1 and 2, and I would say that's a pretty good, like, if you're down to those 2, that's pretty good. I would pick number 2, and the reason is both of them have 4 donating groups, but the OH is going to be a lot stronger donating than the R group. So this one would have a stronger donating group than this one would. So this one's going to be the crappiest here. All right. Now we're going to flip our logic backwards almost. Like, same logic, I guess, but think of it backwards. We're looking for the most reactive diene. So dying wants what kind of group? Yes, so now this one wants donating. So I'll give you a second to look at these answer choices and think about it. Just so maybe if you want to draw it out or like tell me what each of these functional groups are, I'll give you a second to like look at it. When I say I'm going to give you a second, I need to just stop talking and not talk through the whole minute, but whatever. Oh, what did I do? Go back. There we go. Alrighty, I think that was enough time to like look at them. If anyone wants more time, you could feel free to let me know. So, this first one, what functional group is that?
Rosemary,
Yes, what's up?
with the previous problem, the CN double bond one,
Yeah.
is that a diene?
Yes, so it is going to be a diene because one, the CN would be a triple bond actually, and triple bonds aren't going to count as wait, I'm sorry. Say that one more time. I think I heard you backwards. Did you say it's a diene or a dienophile?
Is it a diene because it's an electron drawing group?
No. So all three of these are going to be dienophiles. And the thing that makes it a diene versus a dienophile is not like what group it has attached to it. Because you could have something like this existing. It sucks as a dienophile, but it still could exist. So think of it as it's a dienophile because it has this double bond in the middle. Versus this one has a diene in the middle. Did I answer your question? Because I have a feeling I did. Say again?
Yes, it does. Thank
Okay, cool. Did you say something, Taylor? I thought I heard your voice. Never mind. I see that your mic is off. Okay. So, what group is this? What is this? What functional group? I dropped something and now it's like I can't find it and it's stressing me out just a little bit. But it's whatevs. Guys, come on. I know it's a Wednesday. Yes, it's an aldehyde. So remember COH equals aldehyde. What about CO2H? Mm-hmm. Carboxylic acid. And what about CO2CH3? Ester, exactly. All right, please know these. These will help you on the exam, I promise. Okay. So the aldehyde. Is this donating or withdrawing? I thought that just said ew, and I was like, I get it, Taylor. It's gross, but you don't have to just say ew. You're correct. It is an electron withdrawing group, though. Yay! What about the other side? The R group. It is an electron donating group. Cool. But we have a much stronger, like, withdrawing group than we have a donating group. But that's more chapter 15, so don't worry about it. NO2! What do we think? And would anyone like me to draw them NO2 so they have an idea what it looks like? Electron withdrawing. Ooh, we got some. Okay. I will draw it out because I think once you see it drawn out. Ah, wait. So look at that mess right here. First of all, it has a plus charge here, and there's no lone pairs. And it has all of these electronegative groups on it, and no lone pairs, like I said. So this is going to be a really, really electron withdrawing group. Does that kind of make sense why this is withdrawing versus like OH being... Okay, cool. CH2OH. What does that mean? And I'll draw it out just so we see it. Bam. It just looks like this. Yeah, it's just an alcohol. You're right. So we have this bend here, though. So when we have that bend, is this alcohol donating its lone pairs? No, it's not. Okay. So we have very lightly donating from that CH3. And we have very lightly donating from this electron donating group. All right, last but certainly not least, OH. We talked about this one already, but what do we think? What kind of group is it? Donating group. I 100% agree with you. So, this one has one strong withdrawing, one weak donating. This has two strong withdrawing. This one has two weak donating. And the last one has two really strong donating groups. So which one of these is the best dying or the most reactive dying? Okay, someone said 2. Someone said 2 and then said I lied. And then someone said 4. And yes, we are going to say 4. Because again, we're looking at dying now. And dyings want electron donating. So the best dying would be number 4. Yay! How do we feel about this? Good. Okay. Alright, so the last one we'll do about Diels-Alder, I think, is this one. I think this is the last question I have. So, which of the following dyings can undergo Diels-Alder reactions? So, essentially, what it's asking you is, which of the following are S-cis or can be turned into S-cis? So, I'll give you a couple seconds to look at it, and then we shall talk about it. That was fast. Anthony was like, I don't need a couple seconds. I got this. All right. So, Anthony, you picked C. Why do you think it's C? Awesome. So the single bond can rotate. I totally agree with you. So in this one, that's the only one that has free rotation, right? This is a huge ring system, and this whole thing is conjugated, so that wouldn't react. This one is locked in the ring, so this single bond can't rotate. This single bond is free, so it can rotate. Again, this single bond is locked in a ring. This single bond is free, though. Why can't we rotate E? Yes, the thing is too bulky. So this tert-butyl group in this class in Orgo 2, the only thing that's going to be considered too bulky to rotate is tert-butyl. So this has to be crossed out, and our only answer left is C.
Mary?
Yeah, what's up?
So terbutyls cannot undergo dialysis.
So here's the thing. They can if they're already S-cis. So if it looks like this, it can undergo the reaction. But if it's like this, you cannot rotate it. So tert-butyl, I'm going to say, cannot rotate.
So you have to see it already in cis formation.
Yeah, it would have to already be in the cis conformation, exactly. Okay, so it is 5:52. That hour went by so fast. We did cover a lot though, so I'm proud of us. We did great. If anyone needs to leave or wants to leave, feel free to do so. And if anyone wants to stay, again, feel free to do so. I'll be here till 8, and I am using the same link. So feel free to come and go as you please. Let me just check. I think there's one person. Oh no, okay. So everyone who was signed up for the 6 o'clock hour is already here. So I can definitely go ahead and start if you guys know what you want to like work on in the next hour. And then Taylor asked like about the attendance. For tutoring, I don't have to send any attendance. I just do it myself. So when I like flipped over to my other screen, I just put like present for you guys. Okay, cool. So if you guys want to take like a 2-minute break, that's fine. If you want to ask me any questions, that's fine. If you want to like pick a different topic, that's fine. Just let me know what we want to do for the next hour. Chapter 14. Ethers and epochs. Oh. Okay.